Hello, good morning, everyone. On the behalf of organizing committee and conference co-chairs, I would like to welcome all of you in the third edition of AAAFM conference at UCLA. The organizers have changed the conference format a couple of times due to the current pandemic conditions. And this year, the conference will be held fully online. So once again, I welcome all of you into this conference. So first, I will just briefly introduce about the conference, and then we will move to our first session, our keynote session. So in this conference, we have 4 different symposiums in the field of material science. So first symposium, functional materials for energy storage devices and conversion devices. Second symposium, fabrication of low dimensional nano and 2D materials. And the third symposium, electronic, photonic, and magnetic properties of the materials. And the last one, like functional composite materials. The overall goal of AAAFM conference is to bring junior scientists, senior faculty, and students together so that they can discuss the research opportunities with each other. Actually, we have very good during the past events, like from during past 2 events when the event was held physically at UCLA. But this time, as the event is going online, so the participants can ask the question either online through Zoom, or they can send through our mobile app. So the questions will be sent directly to the speakers, and they can respond to either live or through the email. So this year we have okay, so this year we have 8 keynotes and speakers who will share their excellent research work during the conference. Actually, due to the time zone difference, some of these speakers are not able to join us. So we hope you will enjoy our keynote sessions. In addition to the keynote speakers, we will have the AAAFM awards. And these awards will be announced like tomorrow in our award ceremony, but just giving a brief, like we have Nakamura Award, we have the Kiger Award, and these are like our award winners. And this will be announced by the committee like tomorrow in our award ceremony. And we would also like to share, like from next year, we will having starting another award on the 2D materials, so that the information for that award will also be shared during tomorrow in our award ceremony. Okay. The most important thing which I just want to mention at the beginning of the conference, so all the participants, you can just download our mobile app, as you can see over here. Either you can search this one into the Play Store, or you can use this QR code. So in the app, you will get the most updated agenda of the conference, as well as if there is any urgent message from the conference organizers. So we will share over the mobile app, and you will get the message prompt message. And if you want to ask any questions, or you want to have the discussion anything, so you can use this app for that purpose as well. And in order to access the Zoom links, because this year the conference is totally online, so you have two options. Either you can go online in your account, log in, and then you can just go to overview conference agenda, and then you can click on the external resource and you can go, this will redirect you to the Zoom link, or you can use it through the mobile app, which I just mentioned. And we will broadcast this one on our YouTube channel. So if anybody is not joining the Zoom due to the time zone difference, so they can even listen to the talks after the conference is over. So now I will finish this one, and I would like to welcome Professor Yori, who is the session chair for our first keynote session. So he will take care for that session. So Professor Yori, please, you can start our keynote session.
Well, good morning, good afternoon, good evening, everyone, wherever you are. I know we have a very international audience. And my name is Yuri Gagotsky. I'm professor of material science and engineering at Drexel University in Philadelphia. I'm also directing the Aged Drexel Nanomaterials Institute. And I'm one of the organizers of this conference. And it's my pleasure to chair this first plenary session with 4 excellent speakers. Everyone speaking today, Professor Rodney Rueff, Professor Andrea Ferrari, Professor Paul Weiss, and Professor Richard Kainer are top scientists, very highly cited, very well known, recipients of numerous awards, fellows of multiple professional societies, and hardly any of them needs a detailed introduction. So I'm not going to list all the awards and recognitions. I'm sure you all recognize the names and are probably familiar with much of the work they published here. I'm just going to move us to the first speaker. It's exactly 10:20 a.m., time to start. And our first speaker today is Professor Rod Rueff, who is a distinguished professor at UNIST in Ulsan, Korea, and director of the Institute of Basic Science, IBS Center for Multidimensional Carbon Material. And no one who works in the field of carbon material has not read papers by Professor Rueff. He is clearly a leader in the field. So Rod, please share your screen and let's move to the presentations. Yeah, it's all good now.
Liquid metal composites and work that built up towards and then achieving F-diamine. So we're approaching midnight here in South Korea, so I'll try to make a lively talk nonetheless. So I'd like to give a brief introduction to UNIST and the IBS. Both institutions are 10 years old. I'll talk about the scientific topics, but I'm going to blend in just for a minute or two about transparent peer review, which I'm now a big advocate of, having been essentially forced to be, as I'll mention. So let's get underway where we talk about little liquid metal composites with carbon fillers, our work on single crystal metal foils, how that led to single crystal copper nickel foils. And then how we use these foils to obtain single crystal graphene at low nickel concentrations, and then at higher nickel concentrations, large area bilayer and trilayer graphene, which allowed us to then convert the bilayer graphene to make the F-diamine or single layer diamond. And then I'll probably wrap up at that point. That's probably 40 minutes worth of material. So UNIST, we're just in our 10th year. We're located a little bit south of the center of Ulsan City. This is a kind of an overview of the campus. This is looking down on our Central Lake area. We are the fourth Institute of Science and Technology in Korea. Many of you have probably heard of KAIST, and then DGIST in Daegu and GIST in Gwangju. Now we have UNIST in Ulsan. So it focuses on science and engineering, and we're a federal university. Now, with respect to the Institute for Basic Science, that is modeled somewhat after the Max Planck Institute. It has its own Korean flavor. There are 31 of these centers. So the Institute is a governing body in Daejeon, and they're categorized, as you see, math, physics, chemistry. Ours is a chemistry center located at UNIST. And we have several other centers, just to mention, Center for Genomic Integrity is also at UNIST, and the Center for Soft and Living Matter is at UNIST. We have 3 IBS centers. We have life sciences, earth science, and interdisciplinary categories. So the intent is for these to continue to add in number, maybe eventually reaching 40 or 50 centers spread throughout Korea and doing basic science. Okay, briefly, since I want to talk mostly about science today, but I'm now an advocate of transparent peer review. And so I just wanted to mention something that ought to be obvious, which is when done properly, review process inevitably should lead to better science being published. When it's done unprofessionally, it leads to young people being damaged. Both the topics today actually involved unprofessional situations. I don't want to dwell on that, but I could give many other examples from the last 4 or 5 years. So I'm just going to weave this into my talk. This is the first time I've done this. So I now am a very, very strong advocate of transparent peer review and tired of having some manipulations and unprofessional behavior, which hurts our young people. Okay, now going towards science, I'd like to talk about our work on creating composites using non-metallic fillers, and particularly liquid gallium, but also its eutectics, such as with indium and tin. And we published this work in Science Advances at the beginning of the year. So we are the first group to blend materials into liquid metals like gallium, for example, and its eutectics. And particularly we focused on carbon materials. And so I'm going to talk today about graphene oxide, reduced graphene oxide, and diamond being blended into, for example, gallium. Now, this came about because one of our students was working on a different project that's not published yet. So I won't be able to talk about the serendipitous discovery in terms of what was behind it, but she pointed out to me that she noticed that graphene oxide seemed to be wet by gallium. Now, this was a little surprising because we know that gallium does not wet graphite. It typically doesn't wet diamond. And so graphene oxide has oxygen on its surface in chemical functional groups. So that led me to ponder, could we mix graphene oxide into gallium and make new types of composites? And Dr. Chunhui Wang, who was a postdoc in our group, took that challenge on and began to do that first by hand and then by using some different sorts of mixing tools. So originally we would mix with the mortar and pestle, and then we went to mechanical stirring and ball milling. And the viscosity would climb up with relatively modest loading levels of the graphene oxide. But with a ball mill, we could get up to, for example, around 8%. And this material had a kind of a plasticine-like or putty-like behavior. You can see Chunhui here is manipulating and playing around with this putty-like material. Okay. So Chunhui showed in his work that he could cast the putty-like materials, we list them as gallium putty with graphene oxide, into a variety of different shapes. And one interesting thing about gallium is it's like water in terms of its phase diagram. And so I'm going backwards here. There we go. When a gallium is melted, it actually expands, or excuse me, when it freezes from the liquid state, its density is actually lower. And one interesting thing about the putty-like forms that we made is we didn't see that happening. So they keep their shape. And later we realized that was because of the presence of voids in our samples. And the material could expand into the void space. And it therefore differs, even though it has a very low weight % loading, for example, the graphene oxide. Another thing that probably many in the audience are aware of is that gallium, like mercury, will amalgamate readily with many different metals. And so if you put gallium in contact with a lot of different metal materials, it starts to alloy with them. But the putty-like material doesn't leave any residue at all on these different sorts of metal substrates that you see here. So the cross-section showed us that we did have gallium oxide. This is imaging by SEM, and we could identify the regions that were gallium rich and where there would be graphene oxide through such sorts of imaging, along with energy dispersed X-ray fluorescence. Now, one thing that Chunhui learned was that if he took the gallium putty with graphene oxide and heated it, such as on a hot plate, it would expand quite extraordinarily. And this is due, we understand, to the release of interlamellar water that can be between the graphene oxide layers or trapped on its surface, and also carbon monoxide and carbon dioxide, as you see when we did TGA mass spectroscopy. Now, this is actually more than just a swollen ball, because it is the precursor for making the reduced graphene oxide gallium. So what Chunhui found is that if he then kneaded this in his fingers, and then later with the tools that I have just shown you, he could then collapse this back down. The liquid gallium would come to the surface, and he could then have reduced graphene oxide mixed into the liquid gallium. If we tried to start with reduced graphene oxide, it never wetted. It's much like graphene flakes, and the gallium simply wouldn't wet, and so we could never make the mixture that way. So we had to go through this route of gallium mixed with graphene oxide that we then heat treat, reduce the gallium, the graphene oxide into RGO, and then we could make putty-like materials with it. So this is just showing, again, this expansion that takes place in a couple of other different forms. So one thing we did is we ended up testing rather extensively EMI shielding, for example, with the RGO mixed in, found out a very high performance at moderate thicknesses on different sorts of substrates like paper, for example. Then I got the idea of, well, why don't we mix in diamond? Diamond has tremendously high thermal conductivity. Maybe we can make a very high quality thermally conducting paste or putty-like material. And in our work that is published in Science Advances, we found out that particles smaller than the size shown here wouldn't mix, but once they got up to about 8 microns or larger, then they could be mixed in. And we have a rationalization for this, which is discussed in some detail in the paper. But the mixing is a consequence of the formation of a very thin layer, a few nanometers thick, of gallium oxide. If we attempt to do a preparation of these putty-like materials in a glove box, for example, it doesn't work. So if we're mixing with air or water vapor in air, for example, then the mixing is taking place and is effective. But if we're mixing without oxygen present and without the formation of this skin-like layer of Ga2O3, then we can't make these sorts of composites. We since have learned how to mix in small particles, but that's another story. That's work in progress. So as you're seeing in these cross-section images, we could actually identify this thin layer of gallium oxide formed, for example, between relatively large diamond particles and the surrounding gallium. And so without that skin-like layer, formation of these composites is not possible. So indeed, we did end up learning that the thermal conductivity was very good with RGO in terms of enhancing beyond the value of about 40 watt per meter Kelvin for neat gallium. And diamond was even better. And diamond was also, as expected, more isotropic. And so the reduced graphene oxide tended to be a higher thermal conductor in plane, and for thermal spreading also the conductivity was higher in plane than through plane. So I'd like to thank the co-authors, and one very nice thing about UNIST is I mentioned basic science, and that's our target always is basic science in our center. But when we do have interesting possibilities for applications research, they're typically very talented neighbors who are experts in, for example, thermal interface measurements like Professor Jason Lee, and or thermal conductivity measurements like Professor Gun-Ho Kim and his postdoc Shalik. So often we can have very useful collaborations on applications areas with our UNIST colleagues. So coming back to this little issue that I mentioned at the beginning, why transparent peer review is so important to me now. This was originally submitted to Science on September 11th, 2019. After it was sent out for review, it was rejected. We were encouraged to submit again if someone else hadn't done the work. We did a lot of work in the lab, and we submitted a new manuscript. And then in the process of the review of our second submission, it came to our understanding that one of the reviewers in the process exploited our first submission to Science and damaged the review process. If Science had transparent peer review, this breach in their review process would have been absolutely impossible. So I really hope that all journals adopt transparent review, including Science. Okay, now switching to the next topic, leading up to Diamane. One of the things that we have done is we have found ways to convert large area polycrystalline metal foils such as copper, nickel, platinum, palladium, cobalt into single crystal through particular sort of heat treatment. And I'll talk about that briefly, but I kind of need to move along to get to F-diamine. And so I encourage, if this interests you, that you might enjoy our article published in Science in 2018. It's a very nice perspective by Professor Rowlett of Carnegie Mellon about our work. Most metals are, of course, polycrystalline, and most metal foils are indeed polycrystalline. So if you buy copper metal foil and were to, for example, do electron backscatter diffraction, you'll see this sort of grain structure. It's polygranular. Now, if you heat this, we found by hanging it in a oven close to the melting temperature of copper, which is 1085 degrees C, so at about 1070 degrees C, and with hydrogen mixed in with argon, then kind of miraculously, it can convert over a very large area to entire single crystal. So the out of plane and in plane EBSD patterns are showing that we have one giant single crystal with 111 being the out of plane direction. So if you grow graphene on such single crystal copper foils, then you can see that after nucleation, all of the islands are obviously aligned with each other. The question then is, for a full film, will they join or not? And after growing full films, we have a lot of evidence that they do in fact join well. So they're wonderful substrates for growing those sorts of materials that might be epitaxially matched with them. Briefly, we could do this with nickel and cobalt, also other close packed metals. We have to be at higher temperature, closer to their melting temperatures. And so we used a different furnace, and hydrogen was still an important ingredient in getting this colossal grain growth to occur in these sorts of materials as well. They're not quite as perfect as copper. They do have some twinning showing up, but there can be large multi-centimeter regions that are single crystal. With platinum, our original effort involved using Joule heating. We didn't have an oven that could go to about 1450 degrees C. And so you can see in the region that was attached to the water-cooled electrodes that we still have polycrystalline material, but in this region, most of it is converted to single crystal, also with 111 out-of-plane orientation. Briefly, another very important part of this work was that Sungwon Jin accidentally left the hydrogen off for one run, and yet we got conversion working very nicely. We then learned that in platinum, formation of vacancies with hydrogen diffusing through the platinum or not having hydrogen present, there isn't much difference. It turns out that the energy barrier for vacancy formation is not, so to speak, dramatically lowered by the presence of hydrogen as it is for cobalt, nickel, and copper, for example. And so platinum was a very useful serendipitous situation where then we realized, oh, maybe that's the role that the hydrogen plays. It sort of lubricates at the grain boundaries to allow vacancies to form much more readily. And that allows grain boundary motion, which allows these large crystals to grow. So after we ended up with our copper 111, we then invented a sort of a straightforward method of making alloy foil that was also single crystal. And we had to do those experiments to find out that that could be done. And so I'll tell you briefly about that because it is a nice segue to the diamine, which we needed to have large area single crystal AB bilayer, for example, to achieve at least an opportunity of perhaps getting the diamine material. So what we would do is I suggested to graduate student Ming Huang, my first PhD student at UNIST, let us dip the copper foil into a nickel electroplating bath. And Ming got very good at this. And the nice thing is every time a nickel 2+ ion arrives at the copper, 2 electrons go through the external circuit. We record those. So the integrated current is a very good measure of the amount of nickel that is plated, which we independently verified by mass measurements. So concentration to 3.5 significant figures in these alloys. And sometimes varieties point out that the commercial copper nickel foils are typically used in maritime applications, very resistant to corrosion by seawater. And they contain some other elements. And so the advantage of this homemade copper nickel single crystal foil that I'm showing you is that it's pure copper and nickel. It doesn't have these other elements that could be perturbing some of the science we're trying to do. So we could grow monolayer graphene much faster on this alloy foil than on the pure copper. So small percentage of nickel from about 0.5 atomic percent up to about 9.5 atomic percent would lead to monolayer graphene growing. And this sort of data that you're looking at here, Raman spectroscopy, is kind of a gold standard these days for understanding how well we're our graphene or growing the graphene or the quality of the graphene. So the maps, each pixel in the map is a chosen parameter, such as a ratio of intensities or the full width half maximum of the 2D peak. And the mapping tells us we have extremely high quality single layer graphene. The dark spots you see here are actually due to cosmic rays. So we have no control over those, of course. Another really fascinating thing about this work was we ended up learning that for that concentration range of nickel, and this was discovered by Hyun-Sub Lim, one of our collaborators through low energy electron diffraction investigations, we actually have a superstructure on our surface that has stoichiometry, or it's a compound, copper 6 nickel 1. And that is either 1 atom thick or perhaps 2 atoms thick. And Hyun-Sub could prove that by varying the kinetic energy. So as we lower the kinetic energy, the electrons penetrate less and less and finally barely into our surface. And so we can say 1 or 2 atoms thick. So it's quite fascinating. And I think these single crystal foils, there will be many opportunities for making interesting alloy structures on their surfaces that might have quite different composition than the bulk. For example, we get this sort of structure when we have a half atomic percent of nickel in the bulk, but we have 14.3 atomic percent of nickel on the surface. When we push the nickel concentration up around 20%, and that was through parametric study by Ming, then we could get a very large area bilayer graphene with almost all of it being AB stacked. And so there's obvious epitaxy with the underlying copper nickel surface, which is lattice matched well to graphene, and for that matter, to diamond. And so we published that work, as you see here, and all of these colleagues were very valuable for us in terms of TM and also showing high quality of the bilayer for it to be a field effect transistor, and some in situ SEM imaging about the growth as how it actually occurs on the surface using environmental cell SEM. So again, spectra and the maps are showing we have very high quality. So now I'd like to turn to the diamine story. And as you see, this was published in 2020. I first mention how we fluorinate our samples. And we do this with a fairly simple home-built setup using xenon difluoride. So we have our sample in this little reaction chamber here. It might be heated to roughly 40 to 60 degrees C. We found worked well. We would put our AB stacked bilayer graphene inside, sometimes with it remaining on the copper nickel as grown. Sometimes we would remove it and transfer it to a gold or nickel TEM grid, which are resistant to attack by fluorine. And then with mild heating of the xenon difluoride, we control the vapor pressure and we can mix in argon. And so Pavel did many parametric experiments. Manav was joining at the beginning of the project before moving to India. Colleagues in Professor Kwok's group did theoretical modeling, and TEM was done by Sukwu Lee with Professor Jung-Hoon Lee. So when we talk about F-diamine or H-diamine, we're talking about a stoichiometry C2F. Now, there could be other structures that might have the same sort of stoichiometry. So the question is, if one fluorinates the AB bilayer and tries to find out what structure we have, what are the methods that can be used? And so high resolution TEM for us was really quite critical. Now, let me give some background. It was Leonid Chernozatansky and colleagues shown here who first published about a diamond-like C2H nanolayer that they named diamine. I think it's a good name. It's a mixture of word diamond and alkane. And in their work, they considered hydrogenation. And in this work with my theoretical colleagues, just shortly before arriving at UNIST, we started this theory work before I arrived at UNIST, showing that up to 10 layers, if they're properly stacked, ABC, it turns out ABC, if you have more than 3 layers, then the calculations showed that the energy of conversion was favorable from a few layers up to about 10 layers. But beyond 10 layers, it started to look like it wouldn't happen. So I do remember at the time, or actually a little bit later, telling this story, my younger boy asked me, Dad, why don't you just fluorinate the top and bottom surfaces of graphite and make big diamonds? So that would be wonderful, but they have to be pretty thin for this to work. So I come to one of the punchlines, tell the story sort of out of chronology. Actually, there was an enormous body of X-ray photoelectron spectroscopy done by Pavel that was critical for setting up the right samples to study by TEM. But the TEM shows unequivocally that we, on the left, have AB bilayer graphene. After we fluorinate, this is with the copper nickel still present, we end up with the CF bond length that is completely sensible. The average is 1.62. That's the same bond length as in CF4, for example, or C2F6, or polytetrafluoroethylene. And the interlayer average for the buckled carbon layers is 2.06 angstroms, which coincidentally is exactly the same as the interplanar separation in diamond. So this TEM beautiful cross-section prep with the fib and then imaging done by Sukwu was extraordinarily compelling. And we could look in different directions and see the sorts of structures that proved that we had this C2F diamine with the sp3 linkages between the layers. Some other images are showing raw and filtered images that if we look at the simulated intensity patterns and compared to the experimental intensity patterns, they're essentially in a perfect agreement, and selected area electron diffraction and simulated through Fourier transform patterns look essentially identical as well. Another compelling aspect was we could obtain electron energy loss spectra or yield spectra. And those were modeled by Sehun in Senkyu Kwok's group. And the modeling also is a pretty good fit to the yields data that we obtained. Let me tell you one little interesting story here. It's kind of fun. In our samples, we don't have perfect AB over centimeters. We sometimes have a patch of tri-layer, for example. In this tri-layer region here, the Raman is telling us next to it, there's a little bit of single layer. Everywhere else is the AB bilayer. In this region right here, where the green cross is, we have ABA tri-layer graphene. So the Raman spectroscopy tell us it's ABA and it's not ABC, for example. Now, we would expect that ABA does not have the correct layering of the carbon atoms to allow the diamine transformation to happen. After we fluorinated the sample, we could come back and find out that the tri-layer didn't convert. So these were under the conditions where this is the C2F bilayer, but this region did not convert because the ABA stacking doesn't allow for it because the carbon atoms are in the wrong positions. So let me check my time here. Well, I need to wrap up soon. I'll just have to briefly tell you, but it's a wonderful story to read about in our published work. It was really the X-ray, the XPS spectra that taught us when we had the right stoichiometry. Let me point out that CH has its peak in exactly the same position as CC, and H itself has no XPS spectrum. So it was a wise choice by Pavel to pursue the fluorinated diamine because the CF bond does have a different peak position than the CC bond. And by doing tilt studies and normal emission studies, we were able to unravel when we had converted all of that bilayer into interlayer bonded diamine material, and when we had not, when we had underfluorinated, for example. So the F1S can be analyzed as can be the C1S, and this is a ratio of a lot of factors here, but basically we can pull out from this the atomic percent of, for example, fluorine. We have sample C is underfluorinated, B still underfluorinated, and finally we get to about 32, 33 atomic percent, and that's the correct stoichiometry. So it was sample A that the XPS was telling us had C2F stoichiometry, and that's what we studied with the high resolution TEM and with a lot of other approaches as well. In the same sense, when you look at normal emission versus at 50 degrees, there's these ratios that I'm showing here that should be very close to values such as 1, and when it's not 1, such as in sample B or sample C, and it's higher than 1, it means there's still some of the sp2 carbon that's not been converted. It's underfluorinated. We also did UV-vis spectroscopy that shows that the band gap is about 3.3 electron volts for this fluorinated diamine. And I'll wrap up with a theory article from Zhongfan Liu and colleagues from Peking University. Now, we have not measured the carrier concentrations, but they modeled the carrier concentrations and found that both electron and hole carrier mobilities for F-diamine at 0 strain are actually quite high. A little drink of water. So I should mention one more thing before wrapping up, and that is Seok-Woo Lee, when he was doing TEM, reported back to us that sometimes when the flux was a little bit high of the electron beam, certainly when he imaged at 200 keV instead of 80, and then we decided 80 was a better choice. He could write, in a sense, and convert in local regions the F diamine back to AB stack bilayer graphene. It would defluorinate. So I think there's exciting opportunities in the future as we make this material larger and larger, or others do, for its application in devices in which conductive pathways could be written over the entire F diamine by electron beam irradiation, for example. So I think that's an interesting opportunity. Another interesting opportunity from my perspective is that I do think that eventually we're going to have this material in very large single crystal area, and what clever chemists could figure out how to cleave that CF bond and grow diamond in large area in the future. I think that's a very exciting possibility.
Rod, I'm sorry to interfere, but it's 10:59 and you have 30 seconds left.
Okay, so we had again our interesting experiences that I won't belabor. The one with nature was particularly miserable. I finally labeled it criminal in a letter to the editor-in-chief. But the good news is Nature now does transparent peer review. They now have that. I know that personally. It's a godsend. It's like a huge, huge breath of fresh air compared to some experience we've had before. I don't want to say I'm upset because we didn't get to publish in this journal or that journal versus publishing in Nature Nanotechnology. I'm upset because we didn't have appropriate professional experiences. I am sure that they would have been if we had TPR. Here's a picture of Teachers' Day back before we all had to wear masks. And that's a day that Koreans like to give the teacher a present, which I greatly appreciated. And I greatly appreciate all of the team members as well as the one I mentioned today. Thank you.
Very good. Rod, thank you very much. It's amazing to see that carbon still brings surprises. New carbon nanostructures are being discovered, and there is always a promise to achieve new interesting properties and potentially new applications. While I'm not sure that transparent peer review will solve all our problems, and there are also issues with it here, we may hear more about this as we also have editors speaking in this session. Unfortunately, we don't have time for questions, and feel free to ask in chat, and Professor Ruoff may be kind enough to answer them or send to him questions directly. It's time for us to move to the next talk. We're already 2 minutes behind the schedule. And our next speaker is Professor Andrea Ferrari. He is a professor of nanotechnology in Cambridge. He is also a director of the Cambridge Graphene Center and of EPSRC Center for Doctoral Training in Graphene Technology. I'm sure many of you have read his classical papers on Raman spectroscopy of carbon materials and numerous publications on graphene. And without further words, Andrea, the virtual space is yours.
Okay, thank you very much, Yuri, for the introduction, and thanks for the invitation to this conference that has been marred by a few issues of being in presence, as everybody else has experienced for the past couple of years. So I take that one of the many A's in the title of the conference is advancement, and the other, and the F is functional, and the M is material. So when I think, most functional materials are, when people think about functional material, they think about take a material and attach some functional group to it. I also consider the fact that we need to take the materials that we have and use them for something. Otherwise, they are not very useful, apart from certainly advancing the career of the professors, but that's and also of the students. So today I want to speak about what I now call the layer quantum materials. That is a new platform for the next digital revolution. I admit the slides are very long, so I will stay within the 40 minutes allocated. So we'll have to chop a few parts of it. So we now all experience, like we're experiencing now during this conference, the usefulness of the telecommunications and the progress that is happening. So the bottleneck, if we look towards 5G that is now coming into 4, is the intra-antenna electrical data that is insufficient. So we need a cost-effective optical connectivity. And if we look at the global mobile data traffic in exabyte per month, when an exabyte is 10 to 18 bit, so this is increased to 160 exabyte in 2025 from 38 in 2019. And it's probably even going to increase even more with the now ubiquitous use of the internet and Zoom meetings. But people may not realize that if we compare the average speeds of 3 and 4Gs, they really dwarf with respect to what is happening with 5G communication. That are bringing an enormous amount of data, much more compared to the 3G and 4G standards that we are used to. The other bottleneck is the intra-data center optical transceivers that need to migrate from 400 gigabit per second to 1,600 gigabit per second and a much lower cost per gigabit per second. And in fact, again, we believe, because we are the users, that most of the traffic is between ourselves and the data center, but in fact is the intra-data center traffic that is taking the largest amount of information and growth over the years. So the traffic within the data centers is at least 3 times larger than the one experienced within the users. And what happens after 5G? We are already thinking about the 6G that will fill the gap between the future societal needs and the communication. So bring a new spectrum of technologies where artificial intelligence, Wi-Fi, low latency for transport will all be bundled together. So it will be like 5G on steroids. It will be another 1,000 times increase in speed. But most importantly, there will be massive use of artificial intelligence and energy efficiency. So the 6G is the convergence of 5G, AI, data analytics, and Internet of Things. So if we proceed, hopefully you are seeing the screen okay. Is everything fine? Yeah, I guess so. So we need to overcome some issue. If we look at the next few years, the cost has to be reduced by at least 75%, but most importantly, the speed has to be increased at least 100%, and the consumption of energy has to massively reduce. What people do not realize that already nowadays, the telecommunications, data and communication is accounting for the same emission as the airline industry to the global emissions, CO2 emissions. And by 2040, it will account between 14 and 20%. We consume 17 picojoules for every bit of information that we use. So this conference today will produce kilograms of CO2 just because of the Zoom connections that we're using. An email attachment with maybe 50 megabytes of attachment produces about 300 grams of CO2. So we are not really conscious of the fact that it's data communication that is having a lion's share in these emissions that we need to abate. So graphene is key because it delivers a multiple amount of performance improvement We can have ultra-fast and ultra-efficient electro-optical effects in compact device areas, which brings ultra-high bandwidth density. We can have volume scalability and processability on waveguides, which reduces the cost. We can have uncooled operation, room temperature operation, which contributes to low power consumption. And most importantly, graphene is completely wavelength agnostic. So it doesn't care what wavelength you're using. It behaves the same, most of them. So we can have multiple optical lanes within the same device designed in a photonic integrated circuits. So the same piece of graphene can work at all optical wavelengths. So the graphene has no band gap, so there is no cutoff. The optical absorption is governed by interband and interband transition. So in the simplest approach, we have a piece of graphene, we have a level of doping or chemical potential. If we arrive with our photon, and if our photon energy is larger than the doping, it gets absorbed. If the photon energy divided by 2 is smaller than the doping, it does not get absorbed, and this will create our basic modulation. However, we have the bottleneck that is the intraband absorption. We can always have this intraband absorption, and those are essentially related to the disorder in the material. So if we plot the absorption, we have a constant 2.3%, which is sort of very well known. And then we have this line that should go down to 0. It does not due to the intraband transitions. And then we have other effects happening in the terahertz that I'm not going to discuss today. So this behavior can be described using the Kubo formula, which really does not, I mean, it looks like a complicated equation, but it's not, because it's a few trigonometrical formula. T is the temperature, Kb is the Boltzmann constant. Really, it all depends only on the Fermi level and on this parameter tau. So what is this parameter tau? Is the scattering time. And the scattering time is essentially related to the mobility or to the amount of defects or scattering defects in our sample. So there is a simple formula that is very, very oversimplified. So it's not perfect, we know about it, but it functions as a good rule of thumb. So the mobility of your sample is inversely proportional to the Fermi level and to the scattering time. MVF is the Fermi velocity, which is a constant. And this works if the Fermi level is much bigger than the room temperature energy. So in practice, what does it mean? If we take 10 femtoseconds, it corresponds to a mobility about 200, which is a rather bad piece of graphene of many years ago. If we take 100 femtoseconds, it's a mobility of about 2000, which is a sort of normal piece of graphene that any random person can produce nowadays. And if we take 300, it corresponds to about 7,000, which is a rather good piece of graphene that people can produce. Of course, I'm not discussing here about mechanically exfoliated. I'm talking about something grown by CVD that can be used for large area applications. So if we then consider the dielectric constants, we have the real part and the imaginary part of the dielectric constant. The real part does not change too much with the scattering time. This is plotted for 1550 nanometer, which corresponds to a Fermi level of about 0.5, 0.6. But what happens to the imaginary part, which is important for the phase modulation, is that for 12 femtoseconds, we have a very small, for the sort of absorption modulation, it's a very bad graphene. There is a very small modulation depth. For 100 femtoseconds, there is a bigger one. And for infinite, there is a much bigger modulation, as we would expect in the ideal case scenario. And that's basically all what we need to know. So a graphene modulator is a very, 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 very simple structure whereby you can take a silicon barred waveguide. You can put on it a layer of graphene, a dielectric, another layer of graphene, and you get a modulator. So 2 layers of graphene on top of a waveguide behave as a capacitor. When this capacitor is charged, the charges are accumulated on the top of the waveguide, and so they change the absorption or the effective index of the waveguide. And so when the capacitor is charged, the waveguide is transparent and there is no extra loss. And so there is a significant loss reduction by very, very simple structure. So if we compare silicon with with alternative approaches, silicon is certainly mature technology for which trillions have been spent in the fab development, and photonics is certainly an advantage because it can increase operation speed and bandwidth by using optical interconnection. The limitation of silicon, of course, silicon is not good to detect light. In fact, at the moment, we need another material like germanium on it. And the photonics has a limitation in terms of scalability with the CMOS. So in traditional silicon